afternoon, good evening, class. This is Mr. Arocena, and today I'll discuss magnetic flux and Faraday's law of induction. So last week we just started talking about electromagnetic induction, and we discussed that moving magnets can cause currents to be created because from the perspective of the charge, when it moves, it sees itself as being stationary and sees other things moving past it. Okay, and as we know from the previous unit, if I move an electric charge in a magnetic field, the magnetic field will push the charge. But it turns out that if I move the magnetic field, a moving magnetic field will push stationary charges around. So today we'll discuss a little bit more about that particular phenomenon. All right, so magnetic flux by definition, is the product of the perpendicular component of the magnetic field and the cross-sectional area of the surface in question. Okay. Um, Now, the largest magnetic flux occurs when you have a magnetic field that is entirely perpendicular to the surface of the area, or the area of the surface, surface area. Okay, but in some cases that's not always the case. So you'll occasionally run into a case where the magnetic field is at an angle compared to the surface. So we have to take into account just the perpendicular component, which is given by the cosine of it. So if I were to say, let's draw. Here's my area. Okay, and then I've got a. It's actually a bad drawing. It's kind of hard to see that. So let's do that again. So here's my cross-sectional area, and there's B, and this is my A. Okay, this angle here, that's my perpendicular angle. So this is magnetic flux is kind of how much magnetic field is passing at a perpendicular perpendicular angle to this surface area. Now at an angle, see if I can draw this correctly and see if you guys can visualize this. If my magnetic field passes, let's say this way, then let's see. And I want to draw the angle here, I think. Oops. There we go. There's the angle I want to draw. This is theta. Okay. Which will end up being, this will be theta here. I think that's right. Yeah, that's where I want my angle to be. Or maybe I want it on the other side. No, I think I want it on the other side. Sorry, my mistake. There. Okay. So the angle that I'm measuring is going to be this angle here. That's theta. And I only want the perpendicular component, which is this part here. So using trigonometry, this perpendicular component is the cosine of this angle. Okay. Cosine of that angle. Okay. And then, yeah, that's how we determine how much magnetic flux is going through this particular area. And now, why is that important? Well, it turns out that Michael Faraday, one of the physicists who studied this, noted that the amount of EMF created dependent on the magnetic flux, so basically how much magnetic field is going through the area at a perpendicular angle, and how strong the magnetic field was. Okay. Now, what was neat about this was that as Faraday studied this, he came to the conclusion that in order to induce an EMF, all you need to do is change the magnetic flux, because changing the magnetic flux is the same as moving a magnetic field, right? Because if you move a magnetic field is not usually infinite in nature, so if you move it, at some point you have zero magnetic field. And if for magnetic flux, the same thing can be said. At some points if you have a rotating magnetic field, some points of the at some points of the rotation, the magnetic flux is zero, and some points of rotation, the magnetic flux is not zero. Okay, so it turns out that when Faraday worked with this, he realized that all I have to do is rotate the area. So if I draw a magnetic field going this way, let's see if I can illustrate this. If I draw a magnetic field going this way, and I have an area, a surface area here, some kind of surface area here, and I rotate it around like this, the result of the rotation will constantly change the magnetic flux that's passing through this area. And as a result of that changing magnetic flux, I can then create some amount of EMF. Okay, so if this was an axle, and I rotated this wire through this magnetic field, I would actually generate some kind of EMF. Now, for those of you who've ever worked with small-scale electronics, you'll recognize this rotational motion as a generator. A generator is basically what a generator does. It rotates a coil of wire in a magnetic field, and depending on how fast it rotates, it'll generate some amount of EMF. Excuse me. Excuse me again. Okay, so the rest of this equation is as follows. This is the change in magnetic flux, and this is the time. Alright, so the change in magnetic flux can kind of take two forms. It can either take the form of the rotation, as you see here, because as you rotate, as this rotates this way, the surface area does technically change its area, because if I were to rotate this, then the surface area would end up being at some point looking like this. Stomach my drawing like this, and then the effective area is actually smaller in this rotation than it is over here. Okay. If it's a little hard to visualize, I do apologize. I'll show this in the next lab that we do, just how the area changes. Okay. All right, now we'll revisit the right-hand rule, but this time we'll apply them specifically for solenoids. Now, if you don't remember, I actually don't remember if I mentioned this to you guys, but a solenoid is just a coil of wires. I think I might have mentioned it in the last unit. A coil of wires, like this. Okay, and the arrows in this case represent the direction of the current. Okay. Now, for the right-hand rule for solenoids, if you know the direction of the current, then you can curl your fingers around, around the solenoid in the direction of the current. That'll allow you to determine the direction, or that's where your curl of your fingers goes. And the thumb will then point in the direction of the magnetic field inside the solenoid. I should say inside solenoid. Okay. So in this case, with the electric field going down and then around the upper side, you'd have your fingers curling around this way. So that's your fingers. And if you do that with your right hand, your thumb will end up pointing in this direction. So this is my direction of my magnetic field. It's really handy because then you know where the north and south poles are on your solenoid when you pass a current through it. Right. We'll see this in our next lab, so if you can't quite visualize it with my drawings, then I'll show you in our next lab. Okay, one neat consequence of this changing magnetic field causing a current to be pushed is that this was something that Lenz discovered, is that as you push the electrons, we learned earlier that when you push electrons around, they will actually be able to generate their own magnetic field. And Lenz, another physicist who was studying this, discovered that the magnetic field that the the electrons create as they're being pushed around by this outside magnetic field is in the direction that opposes the magnetic field that pushed them around in the first place. So if you want to think about it, you can say, okay, so if I'm pushing electrons around, I have an outside magnetic field. So the outside magnetic field will push electrons around, push electrons to create some amount of EMF. Now, as a result of this, the moving electrons will generate, geez, my writing is atrocious. They will generate, so the moving electrons will generate another magnetic field that opposes the original magnetic field. Or in this case, I labeled it the outside magnetic field. Okay, so it's really neat. So as you push electrons around, they will push back with the magnetic field that they generate because you push them around in the first place. Now, for those of you in Chem 12, you can sort of think of this as like Le Chatelier's principle, in that in Le Chatelier's principle, if you change the system will work to undo whatever change you caused. So in this case, you push the electrons are now pushing back to try and reduce the magnetic field that's pushing them around in the first place. So it's really neat. Anyways, we'll talk more about this later when we start discussing applications of induced magnetic fields and electric EMF, because it actually has some interesting consequences for things like electric generators or electric motors. All right, and meanwhile, let's go through a few examples of how we can use Faraday's law and this magnetic flux. Okay, so here we have a circular loop of wire with a radius of 2.5 centimeters. It's in a perpendicular magnetic field of 0.4 Tesla. If the loop is removed from the field in a time of 0.05 seconds, what is the induced EMF? So basically it'll look like this. So I will have a circle loop of wire. I'll do a magnetic field. There's my magnetic field. That's my magnetic field. Okay, and then it suddenly changes to this situation where there is no magnetic field. Okay, so the first thing we're going to do then is we are going to draw a writer equation then, actually. So EMF is equal to, or it's not EMF, magnetic flux. So EMF, yeah, EMF is negative N times change in magnetic flux divided by change in time. Now, magnetic flux in this case, so change in magnetic flux is just going to be whatever my final flux is minus my initial flux, and then divided by time. And the great thing about this particular question is that you know what your final flux is. We have one loop, so we'll just go negative 1. Our final flux is 0 because the question tells us that we've removed the loop, so we have 0 final flux. The initial flux can be calculated as B perpendicular times the area, and then we have a time of 0.05 seconds. Now this B perpendicular area thing is going to be our magnetic field, 0.4 Teslas, times the surface area. In this case, we have a circle, so the surface area of a circle is pi times the radius squared. Okay, and the calculator, let's bring it up. So 0.4 times, oh, I should switch to scientific so I can get my pi. So 0.4 times pi times 0.025 squared, close my bracket, equals, oh, that's terrible. So 7, we'll just round to, I don't know, two significant figures. We're not quite in the calculation. So 7.85 times 10 to the negative 4. Excuse me. So that's our flux. So now we get -1. This will be -7.85 times 10 to the negative 4 divided by 0.05. So altogether we get, divide this by 0.05, an EMF of about 0.16 volts. Yeah, so 0.016, 0.016, sorry. 0.016 volts. Yeah, not a lot, but it's only one loop of wire. Okay. More loops will generate more. Okay. All right, next example. Okay, so here we have a square coil of wire, 5 centimeters on each side, and we have 100 of these loops. It's in a magnetic field of 0.02 Tesla, and we rotate it 45 degrees in a time of 0.002 seconds. What is the induced EMF for this particular equation? All right. All right, so I'll write down our EMF equation again. So EMF is negative N times change in flux divided by change in time. We have 100 loops. Our change in flux, so we'll have our final flux minus initial flux divided by 0.002 seconds. All right. Excuse me. Now the final flux will be B perpendicular, or the times A. But in this case, since we're rotating, we'll just go B times A times cos theta, which in our case will be 0.02 Tesla times 0.05 squared times cosine 45. Now, I believe cosine 90 is 0. 45 is something else. All right, so let's calculate this. Our final flux is then going to be 0.02 times 0.05 squared times 45 cos. Yeah, there we go. Equals an answer of 3.54 times 10 to the negative 5. 3.54 times 10 to the negative 5. Okay, then our flux initial will just be B perpendicular A. And we'll assume it's a perpendicular already. And since there's not an angle, so we can just go 0.02 times 0.05 squared, which gives us 0.02 times 0.05 squared. Excuse me. 5.0 times 10 to the negative 5. Count that, make sure. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, negative 5. Okay. So now we get our EMF will be negative 100 divided by 0.002 times 3.54 times 10 to the negative 5 minus 5.0 times 10 to the negative 5. Altogether we get, okay, so, oops, negative, geez, okay, that's weird, 100 negative divided by 0.002, right, 0.002 times, we got 3.54. I'm going to skip the times 10 to the negative 5 since they both have the same multiplier. Let's do this. I'll add in a times 10 to the negative 5 after. Whoops, not that one. Jeez. Okay, I miss my calculator sometimes. All right, so 3.54 minus 5. Okay, there you go. and then I'll multiply this by 10 to the negative 5. So 1, 2, 3, 4. So 0.73. 0.73 volts. There we go. So all those added loops and the extra wire definitely helps out a little bit more. And it's as far as generating more voltage goes. Okay. So as you can see, if you want to generate more voltage, you either need to use more wires or use a bigger area or spin whatever you're spinning really, really fast. Okay. With that, you guys should be able to complete your assignment. Okay. Then we'll be able to, if you have any questions, you guys know how to contact me outside of class. I'll try my best to answer you guys later today. If not, find me tomorrow. All right, good luck and have